like, yeah, subscribe.
Hey y'all, welcome back. Today is our second day of reviewing topics that you studied in Algebra 1 and Algebra 2. Last time we looked at how to solve linear equations, how to solve quadratic equations, and we used a variety of properties to do that, such as the properties of equality, the distributive property. We also used the zero product property, and we talked about factoring. Today we're going to look at and review how to solve power equations, and with a particular interest in when that power is a fraction and just kind of working with fractions. We're also going to look at how to simplify expressions that have square roots, how to rationalize the denominator, and really just I want you to be comfortable working with expressions involving radicals, that little check mark square root symbol. So let's go ahead and dive into it. So a power equation is one that's in this form right here, this x to the a equals b, where a and b are constants and x is your variable. So for example, let's say you had an equation like x, I don't know, cubed equals 12 or something like that, and we want to figure out what x is. To be able to solve an equation like that, you need to know a couple of different properties. Particularly, we're going to work with our exponent properties. You do need to know that when you raise a power to a power, you multiply the powers. Okay, that's really important. You also should know that when you multiply a fraction by its reciprocal, it equals 1. And then when you have anything raised to the first power, it just equals itself. So these are really the three sort of key ideas you need to keep in mind when we're solving these. And this is what's going to allow us to solve equations like this. So the basic idea here is instead of this exponent being 3, we want it to be 1, so that if it's 1, we can just end up saying x equals and we have our number. So the big question becomes, well, how do we get rid of this? Okay, so what we're going to do, and this is just sort of in general, is we're going to raise both sides of the equation to a power. Now you're allowed to do this. This is another one of those properties of equality. If I raise the left-hand side to a power, I need to raise the right-hand side to the power as well. And the particular power you want to raise both to is the reciprocal of whatever this is. So like if this is 3, if we raise it to the power of 1/3, if I multiply 3 by 1/3, I get 1, and then we're essentially done. Okay, so we'll do that to both sides. Now it is possible that you can simplify your answer, and we'll talk about when you can and can't do that. One other thing that I want to point out is that when you're dealing with rational exponents like that, these are equivalent. Okay, so what I mean by that is if you might see an expression written like this, okay, where you have like a root. Now, if you don't see a number here, like if you just see square root of x, that number is assumed to be 2. So I just want to throw that out there. But so that's if you don't see it. But whatever it may be, that number will be the denominator of your exponent. So you can rewrite these radicals as powers with rational exponents. And a lot of times algebraically, it's just easier to deal with terms that are written like this versus like this. So especially next year in calculus, this becomes a little bit more important because of how much you work with rational exponents. But you want to get in the habit of whenever you see something written like this, write it like this. So let's go ahead and look at a few examples here and see how we're going to solve them. All right, so here's some real basic ones. So let's start off with x squared equals 25. Now, you probably were taught originally to solve this by taking the square root of both sides and including that plus or minus, because not only is 5 squared 25, but negative 5 squared is also 25 too. So you want to make sure that you account for both positive and negative solutions. Now, you only have to worry about that plus or minus if this power is even. If it's odd, then it'll either be positive or negative. It won't be both. So just keep that in mind. Now, I know that that's kind of the way you solved it before, right? Like you would take the square root of both sides, and you'd say x equals plus or minus 5. Right? This is sort of how you're taught in Algebra 1 and Algebra 2 to solve this. But I want us to consider working this out slightly differently, and that is with rational exponents. You're still going to basically do the same thing. It's just I want to get away from writing these radicals, and I want to move more towards writing the exponents like this. So let's, I'm going to go ahead and erase all that. Okay, so remember that these are the same, right? Let me go ahead and erase this because that looks like I'm saying it's not the same. These are the same. So I'm going to basically rewrite, anytime I write something with a square root, I'm going to get rid of that and I'm going to write it using the rational exponents. So how do I get this to be 1 instead of x? How do I undo this square? So yeah, you want to take the square root, but another way to kind of think about this is we can raise both of these to the power of 1/2. Now we still have to do that plus or minus business. But you want to say, okay, well, what's 25 to the 1/2 power? It's 5, okay, plus or minus 5. So my solution here will be x equals plus or minus. Let's see if that's one of our little symbols we can use. Excellent. 5. So the reason why I want you to start thinking about it like this instead of doing the square roots is because when we get to problems like, the second one, it'll be more obvious what you're supposed to do. So if I have like x to the 1/3 equals 2, then what we need to do here is raise both of these to the power of the reciprocal of 1/3, right? Because if I want it to be 1, the only way I can get that, is to multiply something by its reciprocal. Now, when you raise a power to a power, you multiply the powers. So that's kind of why we're doing that and why this kind of works. So the reciprocal of 1/3 is going to be 3. So I'm going to cube both sides. Now, when you raise something to an integer power, you don't have to worry about plus or minus. You only have to worry about plus or minus when you take like square roots or 4th roots or 6th roots or 8th roots, any even root. So let's go ahead and cube both of these. So if I raise, let me, just for this problem alone, I'm going to show a little extra step that I wouldn't normally write. So if I'm raising this to the 3rd power, right? So this is, well, it kind of looks kind of nasty, but when you raise a power to a power, you multiply the powers, right? So I'm going to say this is actually x to the 1/3 times, and I don't think I have a dot for times. Let's see if I can find one elsewhere. Oh, you know what? I'm going to have to pull this up from online. Let's see. Just give me one. Actually, let me pause the video while I pull that up. All right, I got it here. All right, so I'm going to paste that in there. If you're curious on how I get these little math symbols to come up, just reach out to me and I'll guide you through how to do that. So times 3, 1/3 times 3 is going to be 1, which is really what we want to happen. 2 to the 3rd power is 8. So what we end up getting is x equals 8. Okay, so this is where it starts getting funky, right? When you start looking at these radicals over here, especially when you've got powers and a whole lot of stuff going on here, it's just, I think, easier for your brain to process if you rewrite these using rational exponents. So instead of looking at it like this, we're going to write it like this, and then it'll be more obvious what we have to do to solve. So it's always, when you write these as a rational exponent, the exponent's going to be the power over the root. So the root should be in the denominator and the power should be in the numerator. So in this case, it would be 2/5 is my power. Equals 10, the 10th root of 7 would be equivalent to saying 7 to the power of 1/10. So hopefully you can kind of start to see why we want to rewrite it like this. When I go to raise both powers, it's just a little bit more obvious what I need to do here. So I'm going to raise this side to a power, and I'm going to raise this side to the exact same power. And I want to raise it to the power that will effectively cancel out this 2/5 power. So to do that, I want to raise it to the reciprocal power. Okay, so the reciprocal of 2/5 is 5/2. So I'm going to raise both of these to the 5/2 power. So let me write that out. So I have x to the power of 2/5, all of that to the power of 5/2, which is equivalent to just saying 2/5 times 5/2. Oops. There we go. So yeah, I guess I'm kind of leaving this out. I should have just left it in there. I thought I was going to type it, but I think it might just be easier to write it. So we're raising both of these to the 5/2 power. It's not really easy to say that over and over again. Okay. So So this is going to be x to the 2/5 times 5 halves, which you already hopefully know what that's going to end up equaling. But we also, this is going to equal 7 to the power of 1/10 times 5 halves. So we're starting to having to deal with some fractions here. You know, hopefully the numbers will be small enough so that you don't need a calculator to simplify them, but let's just see how it'll work. So 2 times 5 is 10, 5 times 2 is 10, 10 divided by 10 is 1. So that's what we want to happen. We want to end up with x to the first power, because as we discussed earlier, x to the first power is just x. So we've got x equals 7 to the power of this little product here. So we have 1 times 5 is 5, 10 times 2 is 20, so we get 5/20ths. Now that can be reduced. Both of these are divisible by 5. So let's see, that would be 1/4. So this is an acceptable answer. What this essentially is the 4th root of 7, or 7 to the 1/4 power. So you can write your final answer like this, or if you just really like those radicals, you can go and write it like this. X equals, let's see if we can do 4th root on here. I don't know if it's going to let me. Yeah, I don't see. I feel like there used to be more options here. I'm not sure. Where is the square root? Am I just gonna have to draw it out? That's kind of weird. I could have swore there was a square root on here somewhere. I might just be blind today. Oh, here it is. Oh, here's the option. Okay. All right, open your eyes, Mr. Schuler. Here we go. So yeah, you could write it like this, the 4th root of 7. This is an acceptable way to write this as well. Now, the 4th root of 7, we got to think about, okay, let's back this up. Is it going to be plus or minus here? You know, if it's really obvious, like if you're taking the square root or the 6th root or the 4th root, but I don't think it's super obvious, like whether or not that occurs here. But let's kind of follow the logic here. We're going to raise it to the 5/2 power, which really means we are raising it to the 5th power and then taking the square root. So we are actually taking the square root somewhere in here, like in this process. So my instinct says we do need a plus or minus in this case. Now, if you're ever not 100% sure, and I'll be honest, I'm not really 100% sure right now. I'm pretty sure, but I wouldn't say 100. It is not a bad idea to go back and double check your answer in your equation. So let's do that real quick for this one. Whenever you're not totally sure if it's a solution, just plug it back in and see if it works. So we've got, what I'm going to do here is I'm going to just store this 4th root of 7 as my, so that's the solution I'm going to be testing. So to store it, I'm going to hit store, and I'll just pick letter A. Doesn't really matter which letter you pick. Okay, so that way I just don't have to type this over and over again. Okay, so what I want is x to the 2/5 power. So I want that, my solution to the 2/5 power. First, I'm just going to check and see if this works. If it doesn't, we got some issues. And then let me check the right-hand side, the 10th root of 7. So 7 raised to the 1/10 power. Okay, so our solution's good, at least the positive version, because you can see the left-hand side equals the right-hand side. Let's test the negative one. And then really, yeah, I don't know. I'm not sure. Let's see what happens. So we're going to say negative a, I'll put that in parentheses. So if any issues there, to the 2/5 power. The question is going to be, is this plus or minus? My gut says yes, but I could be wrong. All right, yeah, so it is also the negative. And that's because this little denominator is 2, right? Like, so if you rate, here, let's just break it down. Maybe I'll write this out. If you raise both sides of an equation by a power that has an even denominator, you must include plus or minus. I'm going to go over my little cheat sheet here with all my symbols. Where's my plus minus? Plus minus, plus minus, plus minus. Okay, very good. must include plus minus with your solution. So this is like if you take the square root, the fourth root, sixth root, that sort of thing. All right, this is very, very important, okay, because otherwise you're going to miss out on one of the solutions. Okay, so it looks good. So this is how you solve those kinds of equations. Now they can get progressively more complicated. You know, like let's say I had something like, let's hide this calculator. We don't need that anymore. Let's say I had something like, I'll just write it over here, like x to the, I don't know, 2, well, we just did 2/5. How about like the 3/5, and then we have like a plus 10 equals 20 or something like that. So we've got some other stuff going on here. You want to isolate this power first to make it look like an equation like this, to be able to use this little trick. So what you'd have to do on a problem like this is actually subtract the 10 from both sides first. So you want to get rid of everything that's sort of surrounding this powered term using those properties of equality like you're solving a linear equation. So in other words, just treat this as your unknown, solve it like you would a linear equation, and then you can apply this property to finish it off. So there's a couple of problems on the homework that are set up like this, and I just don't want you to be scared off by that. All right. So, and there are some other sort of challenging problems on the homework. We could talk about those in class, but I encourage you to give it your best shot. So let's talk now about square roots. Okay, we're going to kind of shift gears here a little bit. Just a little bit. I mean, we're talking about square roots here, but what I want you to know how to do is to simplify a square root properly. So this is something that comes up in geometry and algebra 2, but we're going to revisit it here again. So a square root is considered simplified when the number underneath the square root symbol, or what we call the radicand, has no perfect square root factors, other than 1, obviously, because every number has a factor of 1. And also another little catch to this is that the denominator is not allowed to have any square roots. So you have to do something to take care of that as well. But let's focus on the first half of that, which is that the radicand has no perfect square root factors. So first, just a couple of rapid fire questions here. You know, is root 9 times root 4 the same as root 4 times 9? And we can test that in the calculator real quick. Say, okay, well, that's an easy question to answer. Let's just type it in, right? Like, if I've got the square root of 4, which, wait a minute, that's just 2. We don't need a calculator for this. What's going on here? 2 times 3, is that equal to the square root? Let's see, 4 times 9 is 36. So we get 6 on, yeah, so these are the same. And the question, the real more important question is this always going to be true? And the answer is yes. Okay, the square root of a times the square root of b is equal to the square root of a times b. Now the reason for that is because of our exponent properties. So like I've been kind of really kind of talking about a lot today, is that we can rewrite these radicals as fractional or rational exponents. Let me go ahead and grab that times symbol again. So if I have the a to the 1/2 power times b to the 1/2 power, we have an exponent property. Let's type that in first. That says when you multiply 2 powers, you can combine these. So if it's the same power, we can say that this is equal to a times b to the 1/2 power. Okay. So usually, like in Algebra 1, you would go the other way. Like you'd be given a question like this. It says, oh, you know, simplify this or whatever, and you'd raise each one of these to the 1/2 power. You usually don't take it backwards. But you know, an equality goes either way. So, so this is always going to be true. This is called the power of products property. Again, you know, I keep naming off these properties. You don't need to know them by name. You just need to know what they are and how they work. Okay. Knowing them by name will take it to the next level as far as your understanding to actually know the name of the property. But it's not something you're going to be tested on. So yes, is this, yeah, the answer here is yes. In general, are these equal? Yes. Okay, so the question really is, how do I simplify? How do I rewrite this so that I don't have any perfect square factors in the radicand? So look at this first problem, square root of 24. I should zoom in a little bit. I don't know why those numbers are so small on this slide. Not sure what I was thinking there. Okay, so we got root 24. So you want to think about what are the factors of 24 and are any of them perfect squares? So you might, just make a list. Okay, so 24's factors are 1, 2, 3. And here's a good way you can do it. 1 times 24. Okay, so 1 and 24 are factors. 2 and 12. Yeah. 3 and 8. And 4 and 6. And that's it. Because then 5 is not, and then 6 and 4, you kind of go backwards. So these are my 8 factors for 24. You want to look at these, and we don't really care about 1, but are any of the other ones perfect squares? So when I say perfect squares, I'm talking about something that is, something squared. So like 1 squared is 1, we don't really care about that. 2 squared is 4. Let's see, let's write this, perfect squares. So here's just a list of the first few perfect squares that you should just know that you should be able to recognize this without making this list every time. Oh, let me zoom out a little bit. Yeah, I guess that's not really going to work for me, is it? Okay. Okay, so the perfect squares are going to be 1 times 1 is 1. Okay, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49. What am I at? 8 squared is 64, 9 squared is 81. I feel like I missed one. 2, 3, 4, 5, 6, 7, 8. No, we're good. 10 squared is 100, and so on. Okay, so these are just like the first few perfect squares. Obviously, there's going to be more. Just make a little box here. Oh, whoa, 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 whoa. What's going on here? Okay. These are the factors of 24, okay? So you look at that list and you're looking for the perfect square, okay? So the only perfect square I see in this list, and it says other than 1, they're always gonna have 1. So just forget about 1. This is a perfect square right here, 4. And then it looks like that's my last perfect square. None of these other numbers overlap. So what that means is I want to rewrite this square root as square root of 24 is the same as the square root of 4 times the square root of 6. And the reason I want to rewrite it like that is I can use this property over here, this power of a product property. A nice alliteration on that one. Oh, my calculator's still there. I thought I deleted that one. Get out of here. So that I can split this up, right? So I have the square root of 4 times 6, which is equal to the square root of 4 times the square root of 6. And from here, I can simplify the square root of 4 because I know the square root of 4 is 2. So I'm going to rewrite this as 2 root 6. And this is how we simplify these. That's it. All right. So now our radical is simplified, and I can't simplify this any further. So let's do these next few. Okay, 48, 5. I'm not going to list all the factors here. Really, instead of trying to figure out all the factors, just go through this list and say, okay, well, are any of these factors of 45? So let's see, 4, no. 9 is a factor. What's 9 times 5? So that would have to be the biggest one. So we're going to rewrite this as the square root of 9 times the square root of 5. There we go. And then we're going to split it up, okay? So this would be the square root of 9 times the square root of 5, and the square root of 9 is 3. So we can simplify this to 3 root 5. The square root of 128, similar. Let's see, so 4. If you're not sure, let's see, 4 I think is a factor. Can we get bigger? I don't know. We're going to go back to the calculator here. I like to just like, check. And don't be afraid to, okay, so 128 divided by 4. Oh, come on. Ooh, Mr. Schuler's struggling today. What's the deal with this one? Why isn't one not working? 128, there we go. All right, divided by 4. Okay, so we got a factor of 4, but 32 is has a factor of 16. So let's try 16. 128 divided by 16, we might even need to be able to go bigger than that. 8 still has a perfect square factor, which is 4, so we can even go bigger. Let's try 36. 128 divided by 36. Nope, that one didn't work. How about 16? Maybe I went too far. 128 over 16. I think that might be it. Yeah. Wait, no, we already tried that. For 60. Oh, 64. Oh, goodness. Yeah, obviously. Oh, man. Yeah, 64 is going to be our winner here. So let's rewrite this as, so we'll say equals the square root of 64 times 2 which is equal to the square root of 64 times the square root of 2. And as you kind of get used to this, after you get pretty good at this, you can kind of just jump straight to where you're going. But I want to just show every step. I want to justify how I get from there to there. So the square root of 64 is 8, and then we have times root 2. All right, let's go ahead and box our answer, and that is how you simplify these radicals. Okay, so just check your perfect squares, and find the biggest one that you can divide out. And if you, like, let's say I picked 16. I thought 16 was the biggest one here. If I divide 16 by 128, the other factor is going to be 8, and that should sort of like throw up a red flag, like, wait a minute, 8 has a perfect square factor as well. So, 4. So if you notice that, after dividing one out, that the number left over still has a perfect square factor, go back and see if you can find a bigger number on this list that your radicand is divisible by. Okay, so this is how multiplication of radicals work. Division of radicals works very similarly. Okay, so this is also going to be true. Whenever you're dividing square roots, you can actually put them all under the same square root and vice versa. So are these equivalent? Yeah, it's pretty easy to see that they're going to be equivalent because the square root of 100 is 10, the square root of 4 is 2. So is 10 over 2 the same as the square root of, 100 divided by 4 would be the square root of 25. So 10 divided by 2 is 5, square root of 25 is 5. So yeah, these are equal. So in general, is that true? Yeah, and really for the same reason that this was true. Okay, it all comes back to those exponent properties. Okay, so here's the exponent property that we're utilizing to show that this is true. Let's say we've got the square root of, or no, we actually don't want to write it as square roots. Let's write it using exponents since we're using the exponent properties. A to the 1/2 power divided by b to the 1/2 power is equal to a divided by b to the 1/2 power. This is a power of a quotient property, and usually you see it, again, kind of going backwards, but equations are biconditional statements, right? If this is true, then this is true, and vice versa. So let's go ahead, let me drag that up a little bit, and look at just a couple of quick examples, and then we'll talk about how to rationalize the denominator. We have the square root of 3 over 4 here. Let's zoom in a little bit. See that a little easier. So we've got the square root of 3 over 4. So this is going to be equal to the square root of 3 divided by the square root of 4. Okay, and we know that the square root of 4 is 2, so we can rewrite this as the square root of 3 divided by 2. And then there you go. The square root of 3 is not something that can be simplified, so we leave it alone. Over on the second example, we can split it up first. Okay, so where's my equation? There we go. Equals the square root of 27. Divided by the square root of 16. Now we can simplify both of these. The square root of 16 is 4. Now the square root of 27 is not a perfect square factor. Let me just fill this in real quick. The square root of 27 is not a perfect square, but it does have a perfect square factor. Think of the factors of 27. One of the factors is 9, which is a perfect square. So we could rewrite this as the square root of 9 times the square root of 3. 9 times 3 is 27. Okay, and the square root of 9 is 3. So we've got 3 times the square root of 3 over 4. Sometimes when you do that and you factor out that perfect square factor and you've got a fraction like this, sometimes you can even reduce further. Like, let's say that this number down here was a 6 instead of a 4. Then you could reduce this fraction over here. So if it was 3 over 6, you could reduce it to 1 over 2. And this root would be the same. That would not change when you reduce like that. So the last thing we're going to talk about today is how to handle a situation like this where your denominator is a square root. Because according to our rules, that is not considered simplified unless there's no square roots in the denominator. Okay, now a good reason for that, like a historical reason for that, is it's not really easy to divide by an irrational number by hand. Okay, so back in the day, you would rationalize to make your arithmetic a lot easier. Nowadays, it's not really that big of a deal, but what you'll notice is, like on SAT questions and AP questions, there's lots of multiple choice on these tests, and they'll almost always, not always, but very often will have they'll have their fractions rationalized. So in other words, they won't have any square roots in the denominator. And you have to know that, for instance, 2 divided by the square root of 2 is equal to the square root of 2, and things like that. And so let's go over how to do that algebraically. How do we get rid of square roots in the denominator? So we call this process rationalizing the denominator, and all it is it's just a process that you use to rewrite a fraction that has a square root in the denominator so that it doesn't. It doesn't necessarily mean that you're going to have less terms to write. So saying that it's simplified, it might be a little bit of might make you think that you're not simplifying. It's just, I think I'm being a little confusing here. I guess what I'm trying to say is that it's just a conventional way of writing fractions. In other words, this is just how mathematicians for hundreds of years have agreed that it is better to write a fraction with a square root in a way that it's not in the denominator, just for various reasons. So let's just go over how to do that. It's pretty easy. So here's a couple of quick examples. Let me zoom back out. I guess you can't really see that. Let me zoom that out so you can see the whole thing. So yeah, what we want to do here is we want to rewrite, for instance, 5 over root 2 in such a way so that there's no square root in the denominator. So it's a pretty straightforward way to do that. First, if you've got anything that's not simplified, go ahead and simplify it. Everything here is simplified, so we don't need to worry about this first step. And then second, we're going to multiply both the numerator and the denominator by the radical factor that you're trying to get rid of. So in this case, I'm trying to get rid of the square root of 2. So I'm going to multiply by square root of 2 over square root of 2. Now the reason why I'm allowed to do that is because anything divided by itself is 1, and if you multiply 1 by anything, you're not changing the value of it. So me multiplying this fraction by root 2 over root 2, not like if you throw that in the calculator, you're going to get the same number whether or not you multiply this, because we're just multiplying by 1. Now algebraically, the way this is going to turn out is I have 5 times the square root of 2 on top. Let's go ahead and type this out. 5 times the square root of 2 on top, and on the bottom, I have square root of 2 times square root of 2. So what's 2 times 2? It's 4, right? So we have the square root of 4 on the denominator. And, well, what's the square root of 4? I think you know the answer to that. It's 2. So when you multiply a root by itself, you just end up getting whatever the radicand was with no square root. And that'll happen every time. So as you're doing these, you don't have to show that middle step, but I'm just really trying to show you exactly where this is coming from. Here, let me just copy that, probably easier. So this would just be the same thing as square root of 4, which is obviously 2. So we get this. Now if you have, again, if you've got a fraction here, if this is able to be simplified, I want you to do that. Like again, if this was a 6, 6 divided by 2 is 3, so you could rewrite this as 3 root 2 if that was a 6. But since 5 over 2 is not able to be simplified, there's no common factors there, we're going to just leave it alone. For this next one, let's see if we can, I'm not going to show like these intermediate steps. I'm just going to show that I'm going to multiply just basically this first step and then go kind of straight to the answer unless there's some simplifying to do after the fact. So I'm going to multiply this by the square root of 3 over the square root of 3. Okay, so that numerator is going to be 6 times the square root of 3. And the denominator is going to be root 3 times root 3, which is just 3. So a lot of times it'll be done at that point, but notice how the 6 over 3 can be reduced. 6 over 3 is 2, so this would be equal to 2 root 3. And there you go. So that's rationalizing the denominator. We're able to write these fractions so that there's no square root in the denominator. So just to sort of sum up here, we looked at how to simplify radical expressions by factoring out the perfect square factors. We also looked at how to simplify them when there's radicals in the denominator with a technique called rationalizing the denominator. And we started today off by solving root functions, or power functions, or power equations, rather. And we used these exponent properties kind of all the way through today's lesson. So y'all have a great day, and I'll see you guys next time.